Welcome back to the Explainer. Today, we are building your absolute ultimate mental cheat sheet for mastering 8051 assembly language just in time for the upcoming exam. Honestly, by the end of this, we're going to have the RAM memory map and the PSW concepts locked in so tightly that you'll literally be visualizing these structures in your sleep. So let's jump right in. Okay, here's our game plan for this review. First, we'll hit on why we even bother learning 8051 assembly. Second, we'll map out the 8051 RAM. Third, we're decoding those all-important PSW flags. Fourth, we'll tackle register banks and stacks. And finally, we'll do a hands-on code analysis of stack operations. All right, Section 1, Why Learn 8051 Assembly? Building the Foundation.
Now, you might be wondering, with all the modern high-level languages out there, why are we still studying this? Well, there are 4 core reasons: low-level control, efficiency, debugging, and personal development. It's kind of wild to think about, but the 8051's simple, older architecture makes it the absolute perfect training ground. By learning how to precisely control timing and hardware at this level, we gain this incredibly deep understanding of how microcontrollers actually work under the hood. And you know what? That makes us vastly better debuggers in literally any high-level language we use later on.
Let's move to Section 2, the 8051 RAM memory map, your 128-byte apartment building.
So let's visualize this complete RAM allocation. It's actually fascinating. We only have 128 bytes to work with in total. That's represented in hexadecimal from address 00 at the absolute bottom all the way up to 7F at the top. Just take a second and compare that 128 bytes to the gigabytes we carry around in our smartphones today. It's tiny. But for the exam, knowing exactly what lives on each floor of this little apartment building is absolutely crucial. Let's break down these floors step by step. Step 1, the foundation. The first 32 bytes, from hex 00 to 1F, are strictly set aside for your register banks and the stack. Step 2, moving up a level. The next 16 bytes, from 20 hex to 2F hex, well, that's your bit-addressable read and write memory. And step 3, the penthouse. The top 80 bytes, stretching from 30 hex up to 7F hex, act as the Scratchpad RAM. That's used heavily for storing general data and parameters. Locking these 3 distinct zones into your memory right now is going to be your secret weapon on test day. Section 3, Decoding the PSW Flags, the microcontroller's dashboard. Now we need to talk about the program status word, or PSW. Think of this as the microcontroller's dashboard of warning lights. It acts as our flag register. Interestingly enough, while it is technically an 8-bit register, the 8051 actually only actively uses 6 of those bits to track operation status. Basically, these bits automatically flip to a 1 or a 0 based on the mathematical and logical results of whatever instructions you just ran. Okay, here are the 4 core flags you will definitely be tested on. First up, CY, the carry flag. This bad boy sets whenever there is a carry out from the D7 bit, the most significant bit. Next is AC, the auxiliary carry. This sets if a carry occurs from bit D3 to D4 during an addition or subtraction operation. Then we have P, the parity flag. This one purely tracks the accumulator register, setting itself to 1 if there happens to be an odd number of 1s inside that A register. Finally, OV, the overflow flag. This triggers when the result of a signed number operation just gets too large, overflowing right into the sign bit. Memorizing these specific trigger conditions, that is basically guaranteed points on your exam, for sure.
All right, Section 4, register banks and stacks, bridging the RAM and the PSW.
Picture this. You just powered up the 8051. By default, it automatically targets register bank 0. What does that mean for you? Well, it means if your code simply says to move data into registers R0 through R7, the microcontroller defaults to the very bottom of our RAM map. It's pointing straight at physical RAM locations 0 through 7. But here is where the magic really happens. Let's say we have some standard code loading values into R0, R1, and so on. Because of that default power-up behavior, this data drops right into bank 0 at the bottom of the RAM, right? But what if we execute just one specific instruction first, something like set B PSW.4? By doing that, we are directly manipulating bit 4 of the program status word dashboard. By simply setting that single solitary flag, we literally tell the microcontroller to switch its target to register bank 2. Now, if you run those exact same R0 to R7 move instructions, they're pointing to completely different physical RAM locations further up the map. This is exactly how the dashboard controls the map. It's brilliant.
Section 5, code analysis on stack operations. Let's do a little exam simulation.
Imagine you're sitting in the exam, and you get a scenario like this, examining the stack. What happens to the contents of the registers and the stack pointer after a specific sequence of push and pop instructions? It is absolutely crucial here to actively keep in mind the last-in, first-out nature of the stack. LIFO is the name of the game here.
So say we first load our initial values into registers R6, R1, and R4. Then we hit this sequence: push 6, push 1, push 4. Remember, a push command moves the stack pointer up first and only then drops the data from those specific RAM locations onto the stack. So right now, the value from R4 is sitting pretty right on top. Now look at what happens when we hit the pop instructions. The first one is pop 3. Because the stack is last in, first out, the value that was originally in R4 gets popped off the absolute top of the stack and is placed directly into R3. Make sense? Then maybe we push R1 again and follow with more pops into R5 and R2. The trick here is tracing exactly what value is sitting on top of the stack at each individual line of code. That's how you beat this on the exam. Do not rush it. Sketch it out. Map it out.
To really solidify everything we've covered today, I want you to ask yourself, how can manipulating just a few tiny bits in the PSW entirely change how a microcontroller addresses its 128 bytes of memory? Thinking through that exact relationship, how the flag dashboard directly manipulates the physical RAM map, is the golden key to acing this assembly exam. We've gone over the concepts, you've got the mental cheat sheet built in your head, now let's go crush that test. Thanks so much for joining me on this explainer, and I will catch you in the next one.